All right. Did you get a chance to try any of these questions?
I did this path one, but I think that's about it. That's all I got to.
You learned the garden one?
Yeah.
Okay, that's good. So we had a few questions about this one before. Did you do it all the way to the end?
Uh, if there, I think so. If there was only two parts.
So part A and B, yeah?
Yep.
Well, do you want to let us know how you did it?
Sure. So if we have the total area of the smaller section is 15 meters squared, that part
Yep.
is equal to y minus 1 times x minus 2 because the total area of the concrete, and then we subtract it by the difference.
Okay, so this is y minus 1, yeah?
Yeah.
And this is x minus 2, yeah?
Yeah. So those
So y
multiplied
minus
given us 50 meters squared.
equals 50, yeah?
Yeah. And then I divided it by x minus 2. So I got y minus 1 equals 50 on x minus 2, and then added 1 to both sides to get y.
Yep.
And
Okay, so
I
it's the
think
same
that's
as what
about
they
it.
wanted, right?
Yeah.
Okay, very good. Hmm. Yeah, you have a very clear voice. I like that.
Okay.
Very,
Thank you.
I guess it's the logic that's clear. So okay, so we got that expression, and then what about part B? Y
So
equals
so the area of the concrete will be x times y, and then minus 50 squared.
yep. So you can see the area of the footpath, yeah, is x y minus 50, yeah.
And then we can sub in our value for y to get the paths or the concrete parts area.
And so the area equals 50 on x minus 2 plus 1 times x minus 50, yeah.
And then I put the x into the brackets. So I got 50x on x minus 2 plus x minus 50 is the area.
Yep.
And then I differentiated that using quotient rule.
Yep. Quotient
And
rule. Okay, so um, so okay, so took dA dx, yeah.
yeah,
Okay, so how would you do this?
I got it as 50 outside of x minus 2 and then minus 50x.
50 outside of right, sorry. So you got 50 outside of and it's a fraction.
Outside of x minus 2
X minus 2.
over. Oh, wait, no. I did it a bit differently to how you're trying to do it here. I didn't take the 50 out yet.
Oh, okay. Oh, I see what you're saying. Okay. 50. Oh, okay, you're saying this, yeah?
Yeah.
So it's differentiate the top and then times by the
And
bottom,
then
yeah?
times the bottom, and then
Yeah.
differentiate bottom times top on the bottom
Yeah.
square.
Okay, and then plus what goes here?
Minus 1 times 50x. So
Um,
minus 50x.
so top minus bottom and bottom squared, yeah? And then what's the bottom squared?
The bottom squared is x minus 2 squared.
Yep.
And then after I expand the brackets and cancel out 50x and minus 50x, I'm left with minus 100 on x minus 2 squared.
That's 100 on x minus 2 squared. Yeah.
Yeah. And then I added, and then the x derived is 1, plus 1.
So that the x becomes 1 and the 50 becomes 0. Yeah?
Yeah.
Okay, good. Alright. And what did you do from here? So minus
And
100.
then to get the area as a minimum, I made sure it's a station. I found the x value for it's a stationary point first.
Yep, so
So I made that equal to 0.
you set that to 0, yeah?
Yep. And then I had and then I had 100, and then I brought the 100 minus 100 on x minus 2 squared over. So 1 equals 100 on x minus 2 squared. And then if 100 on x minus 2 squared has to equal to 1, then the bottom also has to equal to 100. So x minus 2 squared equals 100. And then I undid the square, so x minus 2 equals plus or minus 10.
Okay, that's very good. Some people miss the minus 10, yeah? What's the
And
minus
then when
10?
you add 2 to both sides, you get 12 or minus 8. But since it's like a measure, it's a length, then we can't be minus 8, so it has to equal to 12.
Very good. Yeah, it's been very
And
thorough.
then personally, I used a sine table
Yep,
to make sure it's a minimum.
righto, yep.
Yeah, so I had x, dy dx, 11, 12, and 13.
Mm-hmm.
And then I had negative 19 on 81, 0, and 21 on 121. And 21 on 121.
So, okay, so you have a table. Wait, so did you do 19? Like, what did you say?
So
The
I had
table?
12, and then I had 11 on the left and 13 on the right.
Mm.
And then the top line is x and the bottom line is dAdx.
Okay, yep.
And then when you sub 11 into dAdx, you get minus 19 on 81.
Yep.
And
Okay,
then
so 11, so you get, so you put x equals 11 here. You get, so minus, yeah, so minus 100 on 81 plus 1, yeah?
yeah,
So minus 19 on 81.
yes.
Minus 19 on 81. Yeah.
And then when you have 12, you get 0.
Yep.
And when you get 13, I got 21 on 121.
So minus 100 on 121 plus 1, which is 21 on 121. Yeah.
And then we can see the gradient from the tangents go from negative to 0 and then to positive. So it's a minimum turning point.
The negative means it's decreasing, right?
Yes.
0 and then positive. Yeah.
Yeah.
Okay. So that shows it's a local minimum, right?
Yes.
Um, I guess. So how would you know it's I mean, is it clear it's the absolute minimum?
I'm not too sure, but can we can use the second derivative to find the concavity, I think, on the global.
Yeah. Okay, we can try the second derivative. So what's the second derivative?
Um, so I brought up the minus 100 on x minus 2 to as the reverse chain. Not reverse, just the chain rule.
Yeah.
So then that became 200 on x minus 3, or x minus 2, sorry, cubed.
Oh. Alright, you guys see how
And
I did that? So it's basically like x minus 2 basically acts like x because the derivative of x minus 2 is just 1. And the 100 doesn't do anything, so it's really just 1 over x squared. And 1 over f squared is like x to the minus 2. So the minus 2 comes down, and I can go to 1 more. It's x to the minus 3. It's got that. Okay. Okay, so this thing is always positive, right?
Yes.
Can you explain why it's always positive?
It's oh.
Huh?
I'm just having a look at it. Wouldn't it be negative between x equals 0 and 2?
Yeah, good. So what happens if x is less than 2, right? That's the
Yeah, if
So can
x is
x be
less than
less than 2?
it can't for it to be greater than 0.
Yeah, so if we look at the original question, right? The path, like if x is less than 2, then there's no garden, right?
Yeah,
Because x minus 2 has got to be the length of the garden. If x minus 2 is if x is less than 2, the garden's got negative length,
right.
right?
Yeah, and it can't be possible.
Okay, so then the second derivative is always positive, yeah?
Yeah.
Okay, good. Um, yeah. So I think overall it was a very good solution, and we can all learn a lot from that. There are a few points that we can kind of clean up a little bit, I think. At least just be aware of these points.
Yeah.
So, so this one thing, this so when you have area equals 50, was it 50x on x minus 2 plus x plus minus 50? Yeah. So that's the area formula, right?
Yeah.
Yeah. So I guess the main take home message I want to give is be wary of the quotient rule. Um so you didn't do it wrong. You definitely did it right.
Yeah.
It's just kind of there's lots of usually when you do the quotient rule you can avoid it. Um so so the derivative of these things we're fine with. That's just 1 and then 0, yeah?
Mhm.
Okay. But here this trick will come in handy for lots of things as well. You can write this as so the 50 doesn't do anything, right? So it's just x on x minus 2.
Yes.
Yeah. So what you can do is so there's a more general principle at work here. Like when you have a polynomial, it's kind of the principle behind writing things as fractions. Like if the numerator is bigger than or equal to the denominator, you can write it as a mixed numeral, right?
Yeah.
So it's the same for polynomials. So you do minus 2 plus 2.
Plus
Yeah.
2. Yes.
Okay, and then you get this is 50, and the minus 2 is just 1, right? And then you plus
Mm.
2 over x minus 2.
Okay.
And so then when you differentiate it, um, so can you see when you differentiate it, it's the same as differentiating 1 over x minus 2, essentially.
Yeah.
And then you get and that then you times it by 100, right?
Mhm.
That makes sense? Because the 2 and
Yeah.
the 50 is just spectate, yeah?
Yes.
And the 1 over x minus 2, you just pretend that's a 1 over x, basically. So
Yeah.
it's x to the negative 1, the negative 1 comes out, and then it's the negative 2, the power goes down one more. Okay,
Yeah.
so it's minus 100, which you've already figured this out, but it's good that we get the same answer, right? Yeah, so this trick will be very useful for things like this in lots of different contexts as well, because like in some sense when you're trying to graph like this thing, it kind of feels weird, right?
Yeah.
But when you convert it to this, it's just 1 over x, but with a shift.
Yeah.
Okay. Another thing, um, I guess when you had so we have what was the derivative was minus 100 on x minus 2 squared plus 1, right?
Mm-hmm.
So when you're doing the table, I guess the way I would do the table, I guess 11. The main issue is I guess is that the 11 might be too far away from the 12.
Yeah.
Um, so I usually do stuff like 12 minus and 12 plus.
Right.
Kind of it's a bit more non-committal. It's almost like I don't even
Yeah.
I could, it's a bit more fudgeable, which is a good thing and a bad thing, I guess. But so you got 12 is 0, 12 minus um so I guess the point is it's this thing is so if it's less than 12, then this thing um how do you say it? It's less than 10 squared, right?
Yes.
And if it's less than 10 squared, this whole thing's going to be more than 1 and you're minusing it from 1, so it's going to be negative, you know?
Yeah.
Um And if it's more than 12, then it's going to be more than 10 squared. This whole thing's going to be less than 1, and you're minusing from 1. That's going to be positive. Yeah.
Yeah.
Um, yeah. When I was doing this in school, it felt pretty normal. And now, in hindsight, it looks so fudgeable. Like, if you know the answer is going to be a minimum, you just draw this table without even checking it. But
Yeah.
but ultimately, I think the point is you need to be sure, right? Like,
Yeah.
if you're already somehow sure it's the minimum without doing this table, then you can do whatever you want with the table, right?
Mm.
But but I guess the point of this is actually to be sure yourself that the answer is right. Yeah.
Yeah.
Because I think a lot of people when they do exam questions, they write something and then they hope it's right. You know what I mean?
Yeah.
But
Instead of
hoping
like
is kind
knowing
of
it.
like yeah, and sometimes when they're checking it, they're hoping that finding it's going to be right, so they're not finding any mistakes. But the main point is the truth, right? If it's wrong, you're actually hoping to find that it's wrong as quick as possible so you can correct it. Yeah.
Yeah.
So there's no point hoping something that's wrong is right. Yeah. And so then you can fix it, and then it will be right. Yeah, and there's no hoping. Okay, yeah. Otherwise, that's a very good introduction to the class, Jonah. Um, it's a very strong first move you made.
Thanks.
All right, so yeah, thank you, Jonah, for that. So maybe we can look at some of the other ones together. Yeah. So take a bit more of a discussion style, and it's all recorded. So if you miss something, you can ask for the video. Okay. Yeah. So we're mainly just looking at the calculus questions. Yeah. Hmm. Yeah. So this is one of the ones we left. Yeah, this also gives us a way to see like how well you know this stuff, Jonah, as well, yeah. Okay, so let's start with this question. We skipped this last time. Um, so does this question look easy, hard? Yeah, so for us it might be a little hard just because we just learned all these rules, right? Um, what about what about Slava? What about Jonah? Does this question?
It looks pretty simple. It looks like a reverse chain rule.
Okay, yeah, so that's good. And so what makes you think it's a reverse chain rule?
When we when we turn the square root to the power of a half, and since the x is on the outside as well, we can when we're going to differentiate that, we can bring out the x, and then simplify the power of half or whatever we get.
Okay, I guess you're kind of telling us uh how to also do it as well. So yeah, so the key to this reverse chain rule thing is the fact that um the x squared, right? The derivative of x squared is equal to 2x. Yeah? And we don't really care about the 2. We can create that out of nothing. It's the x, and then the x is actually timesing, okay? So when you have something and its derivative is timesing it, yeah, you can basically delete the thing that's being times, and you can treat the thing that you differentiated as just x, yeah? So then in some sense, this question is equivalent to just doing something like this, yeah? Does that make sense? Because the thing that makes this thing not x, the derivative is present, okay? All right, so I'll give you a few moments to do the question, and maybe we can all like discuss our findings. We can also speculate as to where the 2 marks come from. So Jonah, are you able to write on the screen? Do you have like a writing tool?
I think I can annotate it. It says.
Okay, yeah. If it's easy, if it's not, I'll just do it for you.
Let me try. Can everyone see this?
Oh yeah, yeah. We can see that.
Yeah, okay then. Do you want me to do it now?
Oh yeah, yeah. Let's everyone do it, and let me know when you've done it.
Okay then.
Yeah, I kind of I for the ones that we all know how to do, I'd like to see the setting out more carefully, and the ones that we all have no idea, maybe we can just talk about the ideas. Yeah.
Hmm.
Slava, how you doing? This question gives me a lot of memories. I'll share them with you once you guys have done it. Let me know when you've finished.
I finished already.
Okay. Alright, so while we're waiting for the others, let me just have you used Discord?
Yes, I
Sure.
do.
I'll invite you to our server. Let's see.
Okay.
So this
I've just joined.
is that you?
It is me.
And uh, oh, um, yeah. Um, add. Yeah. So that we'll if you have questions or we have stuff during the week, we'll just put it on here.
Yes, okay.
Um, can you see it? Are you able to? Are you able to? Is it working for you, Jonah?
Yes, it's working.
Okay. Oh, you're typing.
Oh yeah,
That's good.
I'm not typing anymore.
Oh, okay, good. All right, so is that enough time? Shall we discuss? Do you want to show us how you set it out?
Yeah, sure. So I made this equal the integral from x outside of x squared plus 1 to the half.
Yep.
And then using the reverse chain rule, I made it n f of x to the n minus 1 times f dash x.
Mm-hmm.
So I have the derivative of inside the brackets, which is 2x, and then times n, which is 3 1 times 3 on 2 outside of x squared plus 1. And then the 2 and the 2 cancel.
Yeah.
And I made a 3 here, I made a 1 here, so I'm going to drag and replace the 1 and 3. And then I'm going to add 1 to the power, and then I have f of x. And then I add c.
Okay. So you got negative a third.
No. This is just me underlining something.
Oh, a third. Um, x squared plus 1 to the power of 3 on 2 plus c. Okay, so if you weren't able to do that, do you know how you could still check he was correct? Like, how would you check this is correct?
I'm not too sure.
So most of the time, I think when people check if things are correct, they just check if all the steps are correct, right?
Yeah.
But that's only I think that's only one way. I think the best way to check if this is correct is to differentiate the answer, right?
Yeah.
Because differentiating should be easier to do. Like, because chain rule is much easier to do than reverse chain rule. So if you can actually show that this answer is the same, right? So does that make sense? So
Yes.
actually, so if you were to differentiate the answer, that you treat this thing like x to 3 on 2, right? The 3 on 2 comes out the front. The third doesn't do anything, yeah? So 3 on 2 comes out the front, and the power goes down by 1, yeah? And then, but because you treat the seed goes to 0, and because you treated that like x, you have to times it by the derivative of it, right? Which is 2x. Okay. So you cancel out the 3's and the 2's, and you get this thing here. Okay. Okay, congratulations, full marks, and then there's no plus C difficulties. Yeah. Yeah. So I think in principle, I guess in principle, you could just write the answer and then show the derivative was that. Yeah. This gives me flashbacks. Okay, maybe a disclaimer. I never actually did the 2-unit HSC. You know? I did the extension 2, and this kind of question was on the extension 2. Actually, I never imagined this kind of question to be on the 2-unit one, but it's kind of interesting that it is. Yeah. So it was kind of funny, and it was always the first question as well. Like it was literally always the first question. You do some integral, and how we did integrals in extension 2 was literally like we're just kind of eyeballing it. And like, oh yeah, that's like the thing, and then we're trying to like make the fraction and then try to write the final answer. You know what I mean? And then we just write the answer, and that would be like the end. Yeah. Okay, but in extension 1, so that was that the way you were taught to set it out, Jonah?
I just tried to show my working a little bit, but I set it
Yeah.
out as Almost, yeah, pretty much how I would.
Okay, because I guess maybe times have changed a little bit, but when we were doing it, so in extension one, the way they would set it out in extension one, actually, so the one thing that makes this a hard, kind of a hard question, it just says find this straight up, yeah. It used to be in extension one, they would actually say like use the reverse chain rule on x squared plus one. So another way of saying that is like let u. Have you seen this before?
I have, but I'm not too familiar with it.
Okay, so this is called substitution, yeah. So
Okay.
substitution is literally, I guess it's a way to break down reverse chain rule for people who can't just go from the first step to the last step in one go. It pretty much breaks it up into as many steps as possible. Okay, so this is called substitution. So basically, the only thing like with substitution you need is to figure out what you substitute. Right? Once you've figured out the substitution, the rest is just it's routine. It's formulaic. It doesn't require any more inspiration. Does that make sense? So so remember how we said for chain rule we need the derivative to be multiplying, yeah? So here the derivative is x, and x squared plus one is the thing that has derivative x. It has two x, right? So then you would be like, oh, I can let u equal x squared plus one. Okay? So that's like the inspiration. Once you got that, it's all routine from there. Yeah. So it's kind of weird how like in one exam you were forced to do this, and in the other one you just wrote down the answer and didn't do anything. Okay. Okay. So what's the procedure from this? Do you know what the procedure is, Jonah?
Not really, but I know it
Okay.
involves
So
like U dash and all that kind of stuff.
yeah. So we do like just du dx, right? Is equal to what's du dx? 2x. So the whole point of this is that du dx should be something we recognize as multiplying the thing, right?
Yeah.
Okay. And so now we're basically trying to substitute everything in at once. Yeah? So then this thing becomes, so that's root u, right?
Yeah.
And then you kind of have, so this is like um so there's a little bit of abusive notation, but you have um like half du dx. Yeah? And so
Yeah.
the whole point of the Leibniz notation is that it looks like it cancels, so it's one half root u du. Yeah.
Yeah.
Oh, it's half root u du. And I guess the point is it's very easy to integrate u to the power of a half. Yeah. So remember, like if you're differentiating, the power comes down. So if you want to undo that, the power needs to go up, right?
Yep.
So the power goes up. So this becomes, so the power becomes 3 on 2. And you got to divide by it because, so it's 2 on 3, like that. Yeah.
Yeah.
And then obviously you have a plus c. Okay. And I guess the thing that everyone forgets when they're doing this, they forget what?
The C.
They what?
They forget to cancel the twos or the C.
Okay, so let's say we got to here. So what
Oh,
happens if they just leave?
sub U back in.
Yeah, okay. Sub x back in, right? Because no one cares about you. I
Yeah.
mean, not the letter U.
Yeah, I
Like,
know.
yeah. So no one cares about. They cared about x, right?
Yeah.
Yeah. Yeah, so I heard from your dad you had a pretty good teacher at school. It kind of
Yeah.
it's kind of showing. That's showing through. Yeah.
Thanks.
Hmm. Very good. Yeah, so I guess that's very interesting. This question would have definitely been like question one, extension two, and like there's always eight questions. Yeah. And if it was in extension one, it would have said x squared plus one is the thing that you're reverse chain ruling. So for this to be in two unit and not tell you what it's doing, it's kind of like it's a sign of the times, maybe, huh? Maybe it really is advanced. Right, you guys, any questions? So you ready to move on? Uh, I don't know. I guess there's some key takeaway points from that. Yeah. So if you're not sure of your answer, you could just differentiate it. That's pretty key. Yeah. So being able to check your answer is a very valuable weapon. Okay. So being able to check your answer literally allows you to convert time into marks. Okay.
Yeah.
Because when I was doing the test, I couldn't do it completely right the first time. But I had enough time left over. I could go and check the ones that I thought was a bit iffy, and that's how I got them right. I never got them right by being perfect. I got them right by knowing my flaws. You know? Okay. Yeah, so we actually saw all of these ones, right? We didn't get to finish all the multiple choice ones. So we did that one, right? Yeah, so when I say we've done that one, I guess the practical implication is that if you want to see how we did it, it's on video, so just you can ask for it on Discord. Yeah?
Yeah. Okay.
Um, did we do this one? Hmm. Okay, so this is kind of nice. It reminds us a little bit of the this table that Jonah was using, right? To testing which way the turning point was going. But even though kind of it's a bit hard to piece it together now, you can see like the stuff we're doing is all stuff that we went through at some point, right? It's just kind of bringing the most relevant one to the thing to the front at any given time. Okay, the following table gives the signs of the first and second derivatives of a function. Which of the following is a possible sketch of y equals f of x? First impressions, easy, hard, medium. I heard some primary school teacher ban people saying questions were easy because it hurt the other people's feelings or something. Um, but yeah, it's ironic though. I shouldn't let the truth hurt your feelings, even though probably the truth is what hurts people's feelings the most for some reason. Okay. Following table gives the signs of the first and second. Yeah. Anyone want to give me their first impressions, or we'll just go through it together? So maybe Aiden. So could A be the answer? All right, maybe more specifically, for example, can let's just one piece of information. But for A, yeah, for A, is the derivative at -2 positive? Like, is that consistent with A? Do you know what it means when it's positive?
Yeah.
So, like, if you draw a tangent line, right, at that point,
Yeah.
the slope is positive. You know, so positive means it's going like that way. Negative is like this way. You know?
Yeah.
So, is it positive?
Yeah. I think so too.
Yeah. So that part is consistent with A. Yeah.
Yeah.
Okay. Okay. Well, what is it not consistent with?
Oh, positive too.
Um. You mean this thing?
Yeah.
So, so you're saying this is this? Yeah, can you see it's still kind of going in that direction? So it's still positive over here. Okay, but what are the other options as equally consistent? Can you see one option that's not consistent with that?
B.
Okay, and why is D not consistent?
Positive too. So.
It's going the other way, right?
Yeah.
Okay, so you know the answer can't be D, right? That's good. Kate, what do you think of B? Is B consistent with all the information? Where is it inconsistent? It's going down, right? Okay, that's good. So so we've come to the same conclusion as Slava. It's A or C, right? And A or C cannot be determined. So we can delete this part of the table now, right? Because they're both consistent. You know? Actually, no. Sorry. This is a little bit of a giveaway, but we can delete this part of the table. Yeah, you probably don't even need the bottom row. So can you see which one it is out of A and C? I'm assuming Jonah already knows. Yes, can you see which one it is? Can you see which one it is? So I guess this thing is a little bit of a giveaway. Well, what does this mean? What does this information tell us?
It's consistent on 0.
So what's happening at 0 that makes it consistent? It's flat, yeah? The derivative of 0 means it's temporarily stopped. Yeah? It's not going up or down. It's just stopped. It's like what happens when the ball goes up and stops going up, yeah? It's flat. Okay, I mean, if you're stuck for time in the test, you might do that, but if we're out of the test, we should probably answer this question a bit more fully. So we should probably understand what this double derivative thing means, right? But this is a weird question. Maybe it's testing like if you know this or this. It's like if you know either one, it's fine. You don't have to know both. So second derivative is talking about it's like the smile or the frown, right? So second derivative negative means like it could still be increasing, but it's increasing at a decreasing rate, you see? So both of them are kind of doing that. Second derivative positive means it's it could be even decreasing, but it's decreasing at an increasing rate. Yeah. Okay, but if it's positive and negative, at some point it's gonna have to be 0, right? So that's this kind of thing. That's this thing. It's called a point of inflection. It's when it changes from negative second derivative to positive negative second derivative. Okay, and then when it's like this, it's called a horizontal point of inflection. Hmm. All right. Any more questions about this?
Nope.
All right. I guess we have 3 questions on the page here. So if you're ever if you're ever done with one early, you can look at the other 2. So maybe we'll set our goal for question 7, but if in the time it takes for everyone to do question 7, you happen to have also done 8 and 9, then we'll include those as well. Okay. Let's do one sec. Alright, what's everyone up to?
I think I did 8 and 9, but I couldn't really figure out 7.
Oh, interesting. Hmm. What about you guys?
37.
Still only 7?
Yeah.
Hmm. No, we all seem to be stuck on 7, is that right? Slava? Hmm. Does this setup remind you of anything?
Um, chain rule.
Yeah, that's how the chain rule setup works, right? It's when functions get composed. That makes sense. So it's asking you for the derivative of this at x equals 5. You know? And so it's basically telling you the chain rule, and here's everything you need to do it. You know? Yeah, I also have another question. Can you see if there's anything wrong with the question? I guess that question won't really be relevant until you've kind of solved it. Do you remember how to do the chain rule? Yeah. So y equals f of g of x. Yeah? I'm doing dy dx. So I'd rather not step in if you can figure it out.
That will equal f dash x times g dash x, but I'm not too sure what to do from there.
Okay, so we say it's f prime. So you differentiate the f as if the g was just an x. Yeah? So that's f prime of g of x. Yeah? And to continue the chain along, it's g prime. Yeah? Okay. So what's the like the next obvious step to do? Usually there's only kind of like one way to go, so it's gonna have to go the right way. Equals 5, right? Because we want to know what is that x equals 5, yeah? Very good. So at x equals 5, this thing equals f prime of g of 5, g prime of 5, yeah? Now what?
They've given us values and then we can sub them in.
Yeah, exactly. So, you see, for example, this g prime of 5, yeah? They give that to, yeah? So what do you get?
You get, they also gave us g of 5, so we have f prime of 1 times 2.
Yeah.
And we also have f prime of 1, which equals negative 4 times 2.
Mm-hmm.
And that's minus 8, which is a.
Hmm. Yeah. So why did they give us this thing here? There must be a common mistake people make that they're trying to exploit. So if x equals at x equals 5, y equals 3, right? It's very strange. So there's one piece of information here that's just so that someone can make a mistake with it. I'm trying to figure out what the mistake is. Hmm. I guess you could sub x equals 5 in too early, but then how would you differentiate that? It would just be 0. Hmm. Yeah, I guess the crazy thing about the chain rule here, like, so in these kind of questions, you generally don't care too much about the assumptions, but like, is f and g, are they really differentiable? You know, are they even allowed to be composed? These kind of questions do linger. So like, so maybe you're like, okay, well, maybe g is not differentiable all the time, but it's at least differentiable at 5, yeah? And f, well, f is at least differentiable at 1, where g of 5 is 1, right? So if f and g were just differentiable at one point, is f of g also differentiable at that point? No? I guess that's the chain rule. So something like that, you might want to know the proof of the chain rule, right? And see if that makes sense, that it's still differentiable. Okay, and then we can maybe, so Jonah, do you wanna kind of explain how you did 8?
Pardon?
Do you wanna explain how you did question 8?
Sure.
Hmm.
So I first rewrote the log as 3 log x base a.
So the log law lets you put the 3 outside, like that.
Yep. And then I divided it by 3, so log x base a equals b on 3.
Yeah.
And then from there, it's just positions. So a is our base, and
Yeah.
to the power of b on 3, which equals x.
Mhm. Yep.
And that equals x, and that's b.
Okay. Hmm. Yeah. Yeah, it's kind of interesting, isn't it? So, so I guess if x equals 1, b would have to be 0, right?
Yes.
Yeah, so maybe I don't want to teach this kind of stuff too early, but there's kind of ways of doing these questions on the exams without fully doing it as well.
Yeah.
So if you look at sort of partial information, right? Like we know that log, so one thing that everyone knows is kind of log of 1 equals 0, okay? That's the same as saying anything to the power of 0 is 1. Okay, so that means if x is 1, which should be like, so, okay, so the b won't be a positive constant, I guess. Uh-huh. But did we really assume b was positive in your proof anyway? We didn't really assume it was positive. Hmm. I guess positive could include 0 as far as your proof is concerned. So if you let x equals 1, b should be 0, but obviously like like if you let x equals 1, b it doesn't have to be 0, right? Let me see. This one, the same with this one. This has the same problem, right? So then you're down to the whether it's a to the b on 3 or a to the b on 3. Yeah, yeah. Yes, you could try to sub in values again to try to figure it out.
Yeah.
Yeah, yeah. So there's definitely ways to do the question without fully knowing how log works, but we'd prefer to fully know how log works. Yeah. Okay. What about question 9? So f of x is any function with domain all real numbers. Which of the following is an even function regardless of the choice of f of x? I guess in maybe a 2-unit advance, they're used to writing the f of x. When you do maths later, we just write f later. The actual f of x is kind of not the right notation because it's easy to get it confused with just like one function value when you put in x. But it doesn't really matter. I think in school, this is this. I think the school syllabus is essentially invented by a physicist because they're used to doing stuff like this to remind them that the function depends on the x. Yeah. Do you know what even means? Remember we talked about this last week.
Yeah.
You know what it means?
Um, positive. So it gives a positive.
Yeah, so it's in general it's this property. If you switch the x, it's still the same. And see, that happens for even powers, so that's why it's called even. If you're squaring minus x, you get x squared. If you square x, you get x squared, right? So which of these is even?
D.
Yeah, so Maybe can you also show why the others are not even? Is it obvious? Yeah, so one thing that kind of allows you. So I think, can you show us you're working for why D is even? Jonah?
Yeah, sure. So we have f of x times f of minus x. And then basically when we swap them, we'll get f of minus x times f of x, which is the same. But then if we
Yeah.
swap it
So
for any of the other ones, we'll get
this is
different
like
x's
G
that
of
won't be
x,
equal.
and this is G of minus x, and they're equal to each other. Yeah. Okay. Okay. So, but how do we prove that they're not the same? So, for example, if I got 2f of x, right, and then we got 2f of minus x, yeah, like these could still be the same, right?
Yeah.
Like f could already be an even function, yeah.
Yeah.
Okay. But the point is, it has to be the same regardless of the choice of f, yeah. So this is where, yeah. So just wondering, yeah, if you want to do extension 2, Jonah, but like how would you prove that 2 times f of x is not even regardless of the choice of f, you know?
I'm not really sure.
Yeah, so when it says regardless of the choice of f of x, right? Basically, you want to make a choice of f of x for which is not even. Okay? So, for example, I could choose f of x, the function to be like it's equal to x for all x. Yeah? And then I get 2x. Yeah? And 2x, well, we want to show that it's not equal to 2 of minus x, right? Okay. But it's the same kind of issue there because, you know, how do you really show that? I mean, it's actually equal when x equals 0, for example, right? So you still need to produce a value of x for which is not equal, you know? So for example, x could be equal to 1, right? And then you get 2, and it's minus 2, right? And they're not equal. So that's a function for which one of the values doesn't agree when you set it to minus. But that proves A doesn't work. So obviously you don't need to prove A doesn't work in this question, but I think we're kind of going beyond the question a bit. Um, yeah. So Jonah, are you still considering doing extension 2?
Yeah, I think so.
Yeah.
But again, I'm not too sure yet.
You'd probably enjoy it, I think. Yeah. You're probably spending a lot of time on extension 1 anyway, I guess. It's kind of uh, it's like okay, so maybe can you guys tell me the something similar for B and C then? Yeah, it's like you just play around with the question a little bit. It's now an extension 2 question, okay? Can you think of a function for b? Um, c? What about it? Is c the negative of b? Um, I don't think there's a typo, but like, yeah, C, I think it's harder to do C than B. Yeah, yeah, C is a little bit different because, yeah, so do you see why B is not odd or even or whatever? They just put a function in, okay? So actually putting in values, substituting like actual values is literally your best friend in algebra, okay? Because that'll let you check anything is right or wrong. Or it'll check you, and then you check anything's wrong, okay? And usually checking something's right is not very different from like checking that it's not wrong 5 times. Things usually go wrong pretty easily. So we can let f be the identity function again. So the identity function just outputs whatever inputs, yeah, for all the x. So then for this function, you see the f of x is equal to the x. So this is just the x, yeah. But then f of x is equal to x again. So this is just x, yeah. So this whole function here is just x. It's just inputting this. It's just outputting the input. Okay. And then if it's just x and you make it minus x, then we've got a situation where minus x equals x, right? So we just minus 1 is not equal to 1. Just pick a value of x. It's not true. Okay, so the part C is a bit more challenging because if you just picked x, like you'll end up with x squared or something, which is even, right? So you might have to be a little bit more tricky. You can't just pick a single x, because it's always going to have an even power if you do. Okay, so you want to somehow get an odd power. Okay, so the way to do that is you can pick x to be like, I don't know, like x plus 1. So there's 2 terms, yeah? And then f of minus x equals minus x plus 1. You just replace x by minus x. And then f of minus x all squared is just this thing squared. So minus x, so it's 1 minus x really, squared. Yeah? And what happens if you square that? So it's x squared, yeah? What else?
Plus 1.
Okay, there's a plus 1. What else?
Minus 2x.
Yeah, good. So you can't forget the minus 2x, okay? That minus 2x is what's going to keep it not even, okay? See, the point is it's an odd power of x and the others are even powers of x. So for example, if you put 1 or minus 1 in there, if you put, okay, maybe not 1 or minus 1, they give you 0. But like, actually, maybe you can do 1 or minus 1. So if you put 1 in here, right? Yeah. You see that'll give you 0. Yeah. Okay. You don't actually even need to expand it. So if you put 1 in here, you get 0, right? Because it's 1 minus 1. If you put negative 1 in here, yeah, what do you get?
2.
You get 2 squared, right?
Yeah.
So it's not 0, but they're different. Okay. So it proves that, you know, A, B, C are not. Yeah. Yeah, the fact that you can let it be any function is literally like crazy, okay? Because there's lots and lots of functions. Okay. Yeah, the fact that it can be any function, if you can't just prove it directly like this, it's likely to be not even. Okay. Okay, so we can skip this multiple choice. The last multiple choice question, we can skip that. We can do that next time. We're gonna do one more of these. So we're also skipping like the statistics for now, yeah? We'll select an opportune time to learn like statistics all in one go. Maybe like in one term. Mm, geometry. Garden question. Some money thing. Oh, okay. Does anything catch your eye? Anything particular you want to do? Oh, this is right up our alley. Alright, if you guys don't suggest anything, we can just do this. Does anyone have any objections or suggestions? Okay, let's do this then. This is right up our alley. We should be experts at this question. Anyone want to share their first impressions? Difficult? Easy? Slava? Looks like a medium hard one. Okay. Now, do you know what stationary points means? Do you remember I used this word already today? What does stationary mean?
Still,
Stopped, right? So what do you think the condition is for stationary points? It's like when you throw the ball up, right? It goes up and it stops. It goes down, right? Stationary. So can you guess the definition of a stationary point?
maybe the value will change.
Hmm. I mean, it tells you what this is, right? So this is going to change a lot, yeah. But maybe there's a moment where it's still, yeah. So a stationary point is where the derivative equals 0. That makes sense? So you might say S or something, but the stationary points are solutions to this equation. So once you know the definition, the rest should be pretty routine. So just apply the definition. So we're trying to differentiate either the minus x sine x, yeah? What have you got so far?
If I differentiate um,
Okay, what did you get?
so I got negative x.
Yeah, it's negative e to the negative x.
Um,
So you could so you basically treat it like e to the x, right?
yeah,
Which just differentiates the e to the x.
yeah.
But then it's not e to the x, it's minus x. You gotta talk about the derivative of the minus x, which is minus 1. So that's the minus 1 at the front. You know?
But it stays as minus x.
Yeah. Yeah, like you treat it like x, but it stays whatever it is.
And then derivative of sine x is cosine x.
Okay. And how do we put that together? Okay.
Sure, that's fine.
Uh, I mean, you could use the quotient rule, but I mean, it's essentially the same. But remember, I try to avoid using quotient rule when possible. So what other rule could you use? I mean, did you use the quotient rule? Oh, you were speculating as to what you could do. Okay. Jonah, Slava.
Product rule.
Yeah, product rule, right? They're timesing together. So you could do sine x here plus e to the minus x cos x, right? Just to show you, you could actually use the quotient rule. How would you use the quotient rule, by the way? Anyone know?
You make it sine x on a to the x.
Yeah, very good. So you make it sine x on e to the x. Yeah, because it's e to the minus x. And then when you do the derivative, you get a quotient rule. So it's essentially this: the top is cos x minus bottom over bottom squared. Yeah. Um, but then when you cancel it, the e to the x cancels once, and then e to the x goes to e to the minus x. So it's e to the minus x cos x minus e to the minus x sine x. Yeah? And it's the same. It's the same thing. Okay. Yeah, so differentiating is definitely a skill you could practice. Yeah. So you just need to put your foot down and be like, I want to be good at differentiating. How am I going to get good at this? I need to put some hours in regularly. Yeah. Um, I don't know. As far as skills is concerned, differentiating, I don't know, like languages is like a 2,000 hours skill. You put in 2,000 hours, you could probably learn a whole language. Differentiating, I don't know. Is it even a 100-hour skill? Differentiating, maybe like it's a 10-hour skill. Okay, so if you put a solid 10 hours in, but the thing is, if you do the 10 hours 1 minute at a time with like a year in between each minute or whatever, you know what I mean? Like it's kind of, you're not really going to get the same 10-hour effect as if you did 10 hours in a row. Um, but you know, like in the syllabus, the very naive syllabus, they allocate 80 hours of class time for extension 2. Okay, the entire course, 80 hours. Okay, so 80 hours is definitely enough to master differentiation. Okay, that's for sure. But 80 hours is not really enough for extension 2. Okay, so I would say extension 2, it's definitely getting in the orders of thousands of hours. Okay, um, I'm not saying just extension 2, like everything altogether. You know, like mastering it. Um, but yeah, but if it were that simple though, anyone could do it, I guess. Then you just call the people who don't do it lazy. But some things, even if you put the hours in, you might not actually master them. You see? Hmm. You heard of that 10,000 hour rule? Heard of it? Yeah. It was kind of funny. It wasn't actually the emphasis of the book. It was kind of another thing, but it was like the guy noticed that um all these Canadian ice hockey players, all the professionals, like the best ones, they're all born in January or something. You're like, it's not really like it doesn't make sense for being born in January to correlate with ice hockey skill, right? So the explanation they came up with was, um, but the ones that were born in like this particular time, they were at the cutoff age for all the team selections. So they always had the advantage because you know, like if you're like trying out for under eights and you're literally 9 years old, yeah, like you have an advantage. So you get picked for that, right? And then when you get picked for that, you sort of get all the extra opportunities that are associated with getting picked for that. So you're playing ice hockey a lot more than the other kids because you're on the team. You get the extra trainings, and then you can maybe make the next team. You know, and over time, that kind of built up to like 10,000 hours worth of expertise, and then these people became like pro hockey players. You know, and it was all just from being born at the right time because they were the oldest kids at the time. Okay, so yeah, I guess it's kind of like, yeah, it's pretty believable that it's a necessary condition. Like to get good at something, you probably need to put the time in, right? But whether it's a sufficient condition, that's the magic, right? Like if all you had to do was mindlessly put in 10,000 hours on autopilot, you know, you could have your headphones in and just maybe even be asleep, just have it playing in the background. If that could be done, okay, you better believe that there's someone exploiting that, okay? Take all the orphanages in the world and make a massive factory out of them. Okay, so it's not really quite the case. And also, if you this is like if you have kind of more like guided reinforcement learning, maybe you can leverage your 1,000 hours and make it as effective as 10,000 hours. Okay, it's not clear if all these things are possible or not. And I guess you're kind of like you're proving it for yourself directly if it's possible for you. All right, I've rambled on too much. We have differentiating functions. What's a natural thing to do now that we got the derivative?
Factorize out e to the minus x.
Yes, very good. See, notice we're trying to solve for equals 0, okay? It's really easy to solve for when things are 0 when it's factored. Because if something times something is 0, then one of the factors is 0. So that's a very good step. So cos x minus sin x. Okay. So this is essentially the calculus part of the question, but and we remember we usually got 1 mark, or at most 2 marks for the calculus part of the question. Yeah. So here's 3 marks. So here's sort of we're solving an equation now. Yeah. So we want to set this to 0. Okay. All right. So what do we do here?
Since e to the x is always positive, there will be no value for that section of the equation to equal to 0.
Oh, excellent. Yeah. That's very good. So we can basically, like, this factor is never 0, so it's only this factor that could be 0, right? Or you can say you can divide by that, or there's lots of ways of getting to this. Okay. You know what to do here?
You can add sin x to both sides and divide by cos x.
Okay. That's equal to 1, yeah?
Yeah, so tan x equals to 1.
Okay, very good.
And then in the triangle, it's 45 degrees.
Okay. So x equals 45 degrees. Is that your final answer?
No, we also have to consider the domain.
Oh, good. Okay. Oh, you're quite on top of this. This is good.
And so it's in the first and third quadrant. So in the first quadrant is 45 degrees, in the third quadrant is 225 degrees.
Yeah. Yeah, see, this kind of thing, yeah, like, there are people who are losing like 1 mark on every question from not considering these things, you understand? You're not missing the solution. So there could be more than one x. Yeah. You guys know tan x? Tan 45 is 1. Okay, so the definition of tan is essentially like this, like, if this is your angle, it makes angle of x with the positive real axis, the x-axis. If that's your theta, then the slope of that radius is the definition of tan x.
Oh, we've done that.
Yeah. So can you see, like, that has slope 1, right? When it's 45 degrees. Yeah. But it also has slope 1 when it's plus 180 more. Yeah. Okay. So 0 to 2 pi just means, you know what 0 to 2 pi means? I have a question for you, Jonah. Do you know why we use radians?
I don't actually, but I just know we use it.
Yeah, so I think it's just to keep the formula looks nice. So if you have d dx sine x, it equals cos x. But it only equals cos x if x is in radians.
Right. Yeah. Okay.
So if it was in degrees, you see there's like some constant term that comes out.
Yeah.
Yeah, so what's our final answer?
I got
So I want final answer, okay? Like satisfying the question.
my first coordinate was pi on 4.
So this is
1
pi
on
on 4, yeah? So pi is 180 degrees, okay? So this is a quarter of 180 degrees. So that's why we say it's pi on 4, yeah? Yep, keep going.
1 on root 2
Okay,
times
so sine, yep, so sine of pi on 4 is 1 on root 2, yeah? Sine of 45 is 1 on root 2, yeah? Yep,
and then multiply that by e to the minus pi on 4. And that's
yes,
our
okay.
first coordinate.
So e to the pi on 4 on root 2, yeah?
Yeah.
That's
And
pi
pi
on
on 4
4,
is our x value.
yeah?
And our second point is 5 pi on 4.
5 pi on 4.
And then minus e to the minus 5 pi on 4 on root 2.
Okay, so yep, so sine of this is now negative 1 on root 2. And then it's e to the minus 5 pi on 4 on root 2. Yeah? Yeah. See, the thing is, if you wrote in your HSC exam literally what I just wrote on the screen, right? Like if I was marking it, I would give you 3 marks. Yeah? Because how can someone really fake this? Like the only way you could really fake this answer is if you basically just copied off someone else, right? See what I'm saying? Because how unlikely is it for you to get pi on 4 e to the minus pi on 2 root 2? I guess you could kind of guess. You could kind of guess. You could kind of guess pi on 4 maybe, but it's still kind of random. Yeah. But the fact that you get to the right answer, like, it's kind of a good indication that everything else is right. Yeah. So maybe in the marking criteria there is like lots of stuff that says, oh, you have to show this and this. But I could definitely imagine someone just kind of ticking along, right? If you like you had all the other stuff there and you got the right answer, someone might see if you got to the right answer first, and then you know what I mean. So the right answer does make a difference, even though these days it's seems to be less and less important, which is not right. Okay, well done. Okay, so we might have to come to a bit of a close. So there's still some questions we haven't done. Some very interesting questions. So we're still focusing our attention to the calculus questions. Okay. So would it be okay if you guys tried that? And I guess if no one's interested anymore, we can switch to something else. But hopefully, if you bring back some more problems, like we don't want to waste this source of questions. They're all pretty good questions, you know. Like as far as we're concerned, these are original questions, okay? Because we haven't done just like tons and tons of exercises. So yeah. Okay. So you guys have any more questions?
No, I think I'm good.
Okay, yeah. Very good first impression, Jonah. And I hope to see you next week. Okay.
Alright, thank you.